Yeah, it's got an almost improvisational tone.
This semester on Stat 201, prepare yourself for YouTube, because we're all zoomed out. Cahoots and special guests, Tiny Brian, Puppet Shark, Evil Moobot,
I am Moobot.
Woody the Rabbit, and more. Super Statistics Bros.
Hey everyone, how are we doing? I'm gonna send out some announcements, see if we can get everyone here. My hair's getting all long again. Time for another haircut, right? There you go. Let's put on a little chill music and say reviewing for final live on YouTube. Okay, click here, and then we'll put the link in. We'll go over to Discord. We'll say reviewing on YouTube currently. Okay. On YouTube currently. I'll see how John's in. At Stat 201. There we go. Let's see. We're doing the YouTube session right now. Crazy hair. Crazy hair. We'll chill music while we get going right here. We'll send out this announcement. Currently reviewing for YouTube now. Okay, that's got it. Boom. Good morning, Kayla. Good to see you here. My hair's looking all crazy. I think it's the weather outside. What should we cover? Take all the notes on what we're covering right here. Let's see. Go bring down this. If you have something you want us to cover, let us know. Say, hey, I'd love to learn about this topic. We can learn about it. Mubot is awake. He's in the chat saying good morning to people. Let's over to the main screen. It's a good question about the final that shout outs to Moira. Moira did the final right here. So it looks like these are all the notes, and we could grab Moira's final right here. And let's go take a picture of what Moira wrote, and let's talk about it. Okay. Here we are with Moira's final. We'll talk about this on what we should know from it. So this is a t-test review. So let's go here to 413 t-test review. So what a t-test is. So first off, you have to know what a t-test is. Does anyone know in the chat what a t-test is? When do we use the t-test? And there's very important things here to let you know if you even look at this problem that it's a t-test. And you would know it's a t-test right here. T-tests are used for means. So you have the 2 sample t and the 1 sample t. If you look at jump output, you can see the difference between a 2 sample t and a 1 sample t, where the 2 sample t compares the means of 2 groups. Like if I want to compare the attack power of legendary and non-legendary Pokemon, we can go here and go to fit y by x, because in a 2 sample t, almost like I'm telling you a test question, you have a categorical x because it creates the 2 groups, because you have legendary, not legendary. That's the categorical x with 2 groups. And then you go here to something like the attack of the 2 groups, and you can see the 2 groups and their attacks. So we have legendary, non-legendary, and then we run what is called the t-test right here. The jump clicks don't matter, the theory matters. And when you get your t-test, you get the following results. So this is the difference between attack power of legendary and non-legendary Pokemon. We can see that a little bit quicker. Hey, Lenny, good to see you there. Notice right here, where does this 41 come from? How do we mathematically get 41? You might not have seen all this output before, but I want you to think through this output on the screen and think, where does 41 come from? Where mathematically is 41 coming from? So see if you can get it. We don't usually give you all this output on the screen, but where in the world does 41 get calculated from? Where in the world is 41 getting calculated from? Does anyone see it? I'll show you in a moment, but see if you can figure it out from this output, because although we haven't shown you this output, you should be able to figure it out. Let's see if anyone gets it. This 41 right here, it says it's the difference. Difference of what? Well, we can go look at the review sheet, and the review sheet is going to help us out a lot when we think about what is the difference. How do we calculate the difference? Does anyone know how to calculate the difference? To calculate the difference, we'll bring this over here. We'll go to the review sheet, the formula sheet. And if you look right here on the 2 sample t, the difference is y bar 1 minus y bar 2. So here's this, and then here's this output. And if you look here, we can put it right about there. That won't block anything of importance that we're going to talk about. We'll zoom in and out a good bit. So this y bar 1, we'll do a nice light purple. And we go right here, and y bar 1 is 116, and I'm just rounding it. The other one is 75. This gets you the difference of 41, because you can see here mean for true, which is true, minus mean for false. Does that make sense for anyone watching right here, how we are getting this value of 41? It is the difference between the 2 sample means. And the standard error down below here in the formula, I prefer to write out the full standard error, like if I'm doing this by hand. The standard error is the formula square root s sub 1 squared over n sub 1 plus s sub 2 squared over n sub 2. And that quantity is actually basically 4. How do I know that? Well, it's right here. You could also go through and use your sample sizes, so you could plug in the n's right here. You usually don't get all this output, but here's n false, which would go there because that's mean for false. There's standard deviation false. So you could go through and literally solve this all out. You could solve all this to get 4. The standard error of the differences is 4, so when you solve this, you get the quantity 41 over 4, and 41 over 4 is a little bigger than 10. It's the t ratio right over there. So that is the t ratio, and that's carrying decimals. I know that that would be technically 10.25, but the t ratio is what we get when we do the difference divided by the standard error. So this is called a 2 sample t because there's 2 means being compared, and the difference of the means is being compared. Now, what you actually have right here are 1 sample t intervals, because we're only looking at the 95% confidence interval for the mean of attack for false, and a 95% confidence interval for the mean attack for true. You could just look at a 95% confidence interval for the mean of all attack. So why is this called a 1 sample t now? It's called a 1 sample t because we're not analyzing the difference in means, we're only analyzing the mean attack power. This is technically now for all Pokemon. So this is why we call it a 1 sample t-test, is because it's just analyzing the mean. T is used for quantitative distributions, and we're analyzing the mean attack. Now see if you can do this real quick. Can anyone tell me the margin of error of this interval right here? If you're watching this chat, or if you're watching this later, see if you can get the margin of error of this interval. Now there's the long way to get it. The long way to get it is going to be the following. The test question would tell you something like the t statistic is equal to, Noel, good to see you there. The test question would say t equals 1.97. Test would tell you that. We don't expect you to know that. For t was 799 degrees of freedom because n minus 1 degrees of freedom. And you'd have to put in here 1.97. So this is the margin of error, which is the quantity after the plus or minus. And then we go here to the standard s over square root of n. So 32.46 divided by square root of 800. Square root of 800 is like 28-ish. So that's going to lead to a quantity of 32 over 28, which is going to get to see Anna, which is going to be about 1.14, 1.15. And then we times that, and that leads to a quantity of a margin of error of how much. See if you can solve this formula right here. And you should get about 2.25. Did anyone solve it? And see if you got it. S, good to see you there. Brielle, good to see you there. Did anyone get a quantity of about 2.25? And then how did I know that? By just doing it. Yep, I'm going to do that one right here. I've got it in the chat. And we're talking about what is a t-test right now. This is a 1 sample t because it's looking at 1 mean. Good to see you, C-Storm. So does anyone solve this? And then how did I know this? Well, while you're solving it, see if you can solve out that equation, but then also watch what I'm about to do. If we know the center of the interval is 79, and so that's the center, and then the upper, which is the upper value of the interval, is 81.25, we can find the margin of error very quickly. We can also say that the lower of the interval is 76.75, and you should be able to see the margin of error now. Remember, the margin of error is the plus or minus on an interval. We're going super light herbal, and it's a joke no one gets but me, which are the best jokes. Go watch Celebrity Jeopardy. And that is what you should get for the quantity all the way down here. We can double check the math, but we should get that. The margin of error is half the length of the interval, and you can see it up there. Nice job, Noel. Yep. And that's more exactly calculated. I'm rounding decimals, and you can go right here and do half the length of the interval. It's a trick we always talk about. I'll disappear so you can see it. But you can solve out this equation to get the margin of error, or you could go right here and take half the length of the interval. The interval starts at the top, which is 181.253802 minus 76.748698. There's the length, and half the length is this right here. Decimal differences might come into play. Clay, good to see you there. So decimal differences could come into play, but this is a t interval. And on the test, we would have to give you the t statistic. I probably didn't carry enough decimals on it. We could go look that up and double check our t statistics with applets. On the test, you won't use applets. We'll just tell you t statistics. Well, thank you, C-Storm. I appreciate that. Very kind of you. And feel free to ask questions if you got them. So shout out C-Storm. We'll throw you some points in the chat. So to the question we have right here on Moira's question, which has disappeared off the screen. 1 second right here. We're going to go find that question. I'll put it on the screen. I swear I did. Here it is. Don't worry, I was up. So the formula for the margin of error is going to vary based on what we're doing. The formula for the margin of error, you can use the theoretical way of solving it, which the margin of error will always equal to the upper minus the lower divided by 2, which is equal to the center minus the lower, which is equal to the upper minus the center. It's half the length of the interval. All of those things right there, the center minus the lower, my C's look like L's. We'll make them really look like C's. Half the length of the interval, because the center is the midpoint. So if you go to the upper, that's a margin of error. If you go to the lower, that's a margin of error. They're distance apart. Really good to understand this theoretically, and just think about what you're seeing here visually when you see the center to the upper or the center to the lower, or half the length of the interval. Wow. Wow. Does that make sense, Noel, right there? The margin of error is half the length of the interval. That is a margin of error. It's half the length of this interval. So you can take the full length and divide it in half, or you can just go to the center and go to the upper and just figure out their distance. It'll always be like a positive. We always express it in the positive sense, or to the center to the lower and express this distance. The more you understand this theoretically, the more you can figure out these formulas when you're doing it. So if we're doing it by 2, then you need to do upper minus lower. Correct, because it's half the length of the full interval. This is the full interval right here. That's the length of upper to lower, and you have to take half that length. But you have to be careful because there are other ways to calculate margin of error if you just have summary statistics. For example, in this question here on the one sample t, you could use the following information. You could use this, and then you would estimate a t of about 1.97, or basically 2. We would have to tell you on the test again that a t with how many degrees of freedom? Someone put the degrees of freedom in the chat for me. This is a one sample t. Very good, quick questions that we should know very quickly. What are the degrees of freedom? What are the degrees? 199, Jackson, nice answer. 199, n minus 1. Remember, the one sample t has n minus 1 degrees of freedom. The two sample t is too complicated. We don't do that formula by hand. It's too complicated. Good work. So and good to see Grace and Bella and everyone. Noah, good job. And so there is 199 degrees of freedom. This is a subscript. It's not multiply. We put a star, meaning based on percent confident. We are picking 99%, 95% confident. And the t would be about 1.9, basically 7. It'll round. We could check a t-applet, but the test would tell you this. So with this information right here, the margin of error would be the following formula. We only care about the plus or minus, so we don't really look at the y bar on it because that's the estimate. The margin of error is going to be everything after the plus or minus on this formula right here. So it'd be, oh my God, I'm zoomed in so close. It'd be everything after the plus or minus, which would be the t-statistic times the standard error, which is really easy to calculate because they give us the standard error, which we could find a standard of y bar technically. So what would we put in here to find the margin of error of this formula? So this is not doing half the length of the interval, David, good to see you. This is finding the margin of error using the information provided. Using the information provided, what would we substitute in to find the margin of error? And the standard error is technically, this quantity is s over square root of n. So you could find this quantity by doing s, which is going to be 12, about 12 divided by square root of 200. That's horrible handwriting. 1.97 is t, correct. And then we plug in the standard error. The standard error is 0.895. So you just plug in those values right there, and you can see the margin of error by solving this. The margin of error is going to be, so 1.97 times 0.89518. And there it is right there. Now, what I would do is you can check this. If I add this to the mean, what value should I get? If I add this value right here to the mean, which is a margin of error, I'm going to add 1.76 to the mean. Don't solve it, but think, what value should I get? This is good theory. Understanding the theory helps you solve the test. If this is the margin of error, and I add it to the mean, I'll get the upper Laney exactly. And we can confirm it by going here and adding 70.98 and add that margin of error, and we get the upper. We could go back to the mean by subtracting and then subtract again and get the lower bound of the interval. Now, there could be small decimal differences, but we are basically getting the upper and the lower. And does that make sense theoretically? If you find the margin of error, like if you believe you've calculated it correctly, then you can go to the center of the interval, which is the mean, y bar, and you can go up from the mean a margin of error and down from the mean a margin of error to confirm it. The more you can confirm your answers and be like, yep, that's the margin of error, I found it, the better you are on the test that you know you got it right. And you can just put a check mark next to that question or write on your sheet of paper, I got number 42 or something, and then continue on. Key to life right there. So Moira starts off this question right here asking about what is the null hypothesis. So let's label this video on how to write your nulls. So this is a lot of good knowledge. Moira did, shout outs to Moira, put W Moiras. I'm gonna throw 5,000 points for W Moiras in the chat. Moira is amazing. She knows her stats, and so huge thank you. You subtract, you get the lower. Nice job. Thank you, Lindsay. So one sample, two sample, two last bar. One sample and two sample t's. Okay. So how do we write the null and alternative? Every time you write a null and alternative, you need to do the following, except for the last chapter. So you will start by writing your null hypothesis. The null always has the what sign. The null always has the what sign. Complete my sentence. Yeah, we'll be doing that here, Noel. The null always has the what sign, the equal sign. So we have here first a population parameter is equal to a hypothesized value. Now, when it comes to doing this, this is used for 3 separate tests, this formatting. We'll talk about the last one in a moment. Great job, everyone in the chat. So the population parameter will be one of 3 things, and you will write this verbatim if you're doing in stat notation. It'll either be P when we test the true proportion, mu when we test the true mean, or mu1 minus mu2 when we test the difference between 2 means. We make Clay a mod. Clay, I don't know why you're not a mod. Clay, you're a mod now. W Clay. So with this right here, the hypothesized value will be something we choose in the problem. You will write a hypothesized value, not you will write a hypothesized value, but if we are doing a test with P, then the hypothesized value will be called what? What is the notation? Mu stands for the true mean. Like if you were to know that the average GPA of all UT students is 3.5, that is mu. Mu is used when you have the full population. Caitlin, no bad questions here. Just ask. Ask right away. If we do a test with mu, what would be the hypothesized mean? So does anyone know if you do a test with P, what is the hypothesized proportion? If you do a test with mu, what is the hypothesized mu? We've got a really quick way of noting it. Well, the null has the equal sign, but what is the notation for hypothesized proportion or null proportion. Sometimes called null proportion, the proportion believed according to the null hypothesis. The Jennifer, good to see you here. I think former student, right? Jennifer, shout outs right there. Good to see you. Shout outs, positivity, Jennifer. Does anyone know? Feel free to say, I don't know. I don't know just shows you're here. I'll give answers away. Don't worry, I'll tell you answers. Take guesses. The more you guess, the more you think, the more you work through it in your head. Thank you, Colin, right there. C-Storm, another C-Storm. So whenever we talk about the null proportion, the null has a close Brielle. Good guess, Brielle. That is sample proportion. P hat is sample proportion. Null proportion is P naught. P naught. What do you think the hypothesized mean is? If mu is the true mean, what do you think the hypothesized mean is? If mu is the true mean, what do you think the hypothesized mean is? Just go by the theory on this. Mu naught. Mu naught. Put commas between these. Mu naught. Great job, Jackson. Nice work. The hypothesized. So the hypothesized mean is mu naught. Now we go a little weird right here on the last one, and they call it delta for change between delta naught. I don't know. You won't see that anywhere on the test. These ones right here, so we'll just erase, we'll leave it there, and we'll put a little like, just pretend I didn't write that. It is in the notes, but I don't think you see it anywhere on the test. Delta naught is assumed to be 0 in almost all circumstances. So here's the thing. I focus so much on writing the null, because whenever you write your alternative, you only change the what. Whenever you write your alternative, you only change your what. Whenever you write your alternative, you only change the sign. And it doesn't want that H in there for some reason. It says no H. No H, lowercase h. You only change the sign. You change this to an A also. I will show you that also. So you only change the sign. And then how do we pick the sign? Based on the data or the researcher's question? I've asked this one 1,000 times, but you should know it by now. How do you pick the sign? Based on the data or the researcher's question? You say, man, my data sure looks like this is increasing. What do? You pick it on the researcher's question. Researcher comes up with their question, and then they collect data. You don't collect data and then come up with a question. Research goes, think about the world, come up with a question, and then collect data to see if it's in line with the null or you have reason to reject the null. So let's try writing a null hypothesis right now. Brian thinks that, historically speaking, he thinks 35% of his students this semester will get in, or 35% of Stats 2-1 students get an A. Brian thinks 35% of Stats 2-1 students get an A. So what's the null hypothesis? What is the null hypothesis? This is just practicing writing a null and alternative right now. Brian thinks 35% of students get an A in Stats 201. Close, Bella. Go more detail. I want the full, like you have to write it out like it's the test, like it's a written test, which we're not doing, but the test says you got to write it out. And you're like, wait, I thought we were doing this test online. I didn't think I had to write it out. I mean, there are written questions, but yes, great job, Lainey, David, and we'll throw great job right there, Bella. And even Jackson, we're throwing Jackson 5,000 points. Jackson even put the null, which I like before it. The null hypothesis states, you might even add a little semicolon right there, or colon. I don't even know what to put. Great job. Brielle has done it perfectly in the chat, and we're just practicing right here, knowing how to write the null. So think about this. When you read this, let's think what it says. Let's read it as a full sentence. The null hypothesis states that the true proportion of students who get an A is equal to 35% or 0.35 as a proportion. So I never stated if I think it's less or more. So what is the logical alternative that we would write now? What is the logical alternative? What is the logical alternative? Like write the alternative, because I never said I think it's less. I never said I think it's more. So Brian just believes that it's 35% and not equals to. When we don't give a sidedness to this, the alternative will be the two-sided does not equals unless the researcher states a preference for it. Great job, Jackson, right there. Unless the researcher states a sidedness to the test. So with this, notice the only thing that changed between this was the sign of the alternative. You don't change anything else. What is P naught equal to, right? P naught equals something like you're reading this problem and you have to solve it. What is P naught equal to? What is P naught equal to? And I'm going to ask you a really tough question after that. What is P naught equal to? What is P naught equal to? What is P naught equal to? There's no button. What is P naught equal to? Does anyone know? 35%. Great job, Brielle, right there. Yes. Because this value over here is the hypothesis, whatever you put right here is the hypothesized value. So it's the hypothesized proportion of students who don't get an A. Like, I just came up with an idea. I think I did it. I can go find it. I did it during office hours. If someone wants to throw that link in the chat here, that'd be great. Help say, hey, Brian did it during this office hours. It was like office hours last week around this time. I did a full review of the formula sheet, and we're doing a hypothesis test. Feel free to ask questions. We're going over Moira's question right here and just understanding the components of this. So when you are figuring out how to write out your, thank you, Lainey. When you're figuring out how to write your hypothesis test, you have to understand what the question is reading. Thank you so much, Caitlin. And with this, let's try a slightly different one. And notice what I can do. I can just erase this. I can erase this. And we're going to do one more big hypothesis test over this. So stay tuned. What if I were to say, thank you, Aiden. What if I were to say, Brian thinks that he gets as many points in a basketball game as his brother. Brian gets as many points in a basketball game on average as his brother. So what would be the null hypothesis there between Brian and Darren? Brian thinks he gets as many points in the basketball game as his brother. Oh, Aiden, shoutouts. That's really good, man. Or, I don't know. Pretty much, Lainey. Pretty much. Lainey's on the right track. Lainey, that's how we would just talk to people. Lainey, that's very good right there. That's basically it. When it wouldn't be... Anna's got it right there. Look what Anna wrote. It'd be the mean for Brian equals the mean for Darren. Does that make sense? Mu Brian points, like Brian's average points equals Darren's average points. Brian's average points does not equal Darren's average points. Does that make sense? So we're talking about like how many points we get on average in a game. And think about this. What we're actually stating by saying they're equal is we are actually saying there is what between them. So focus in on this now. And this, we are saying that their what is what by saying they are equal. So you can write it this way, like what I just did, but this is the classic way of writing it right here. By saying they are equal, we're saying there's no difference, and that is correct, Bella. This is a mu1 minus mu2, and all you do with this is you algebra this over to the other side. That's my preferred way to write it. If you algebra that to the other side, you just get that mean 1 equals mean 2, because mu1 minus mu2 equals 0. Just go ahead and algebra it over to the other side. Does that make sense? What I'm saying right here is like, you can just add it to the other side because you can do plus mu d on the other side, and then you will get that they are equal to each other because the difference is 0, so they're equal if there is no difference. And then it's just a nicer way to write it, but the quantity we are trying to understand right now is the true difference between the means. Like, what is the true difference between Darren and Brian? And the hypothesized value is what? What is the hypothesized value for this? The hypothesized value of the difference is what? You saw it just a second ago. And it's kind of stated in this idea right here. It is delta naught. Good answers, Bella. You are correct. In notation sense, it's delta naught. And Michael, great answer. I was looking for 0. Both correct answers. In notation, we call it delta naught. Won't be on the test. I don't think we've ever done that. Delta naught equals 0. It is in the notes. But it would say delta naught equals 0. The hypothesized difference equals to 0. Or change in means, delta. So does that make sense right there, what we have? And we'll do one last one. Actually, we'll switch it up because now I'm going to throw a trick at you. Watch out for this trick. And let's say Brian wants to analyze where students live and if they pass the class. Okay, so I want you to write out the null hypothesis for this. Be very careful. So Brian wants to analyze where students live on, off, out of state. And if they pass, write the null and alternative hypothesis. Maybe it's a good thing I did that. So Brian wants to analyze where students live on or off campus and where they pass or fail the class. What you want to notice right here immediately as you work through this is that on or off campus is a categorical variable. Pass or fail is a categorical variable, which means you're dealing with count data, which is the fourth condition for a certain test. Students, living location, and passing class are independent. Boom, Noel got it immediately. Yes. This is the one that breaks the mold on how we do it. There are ways of writing it with the classic. This is the independence. This is the chi-squared test of independence. And all you do is say that the two things are independent. And then the alternative would be that they're not independent. And as you look at your formula sheet, realize this, that if you remember, it is the chi-squared test of independence. That word is going to be key when doing the null and alternative hypothesis. That when you have two categorical variables, you will have the expected cell count condition. So there's expected cell count conditions, kind of like a little cheat sheet. Not that you can have a real cheat sheet, but you can have this. The chi-squared test of independence is used for two categorical variables, and all the formulas are right here on the screen. Check out the review sheet we did. So if it's categorical, we use the word independent. When it's two categorical variables. So we'll do one last portion right here. And this is in the other videos, but I'm trying to hit as many topics as I can and segment this video. That is correct right there, Bella. So try this quiz. You're ready? And then we're going to finish up Moira's review, but we're just using it as a template to help us. Okay. Let me ask you this. This is tools and technique. What test would you use? This is just using tests, okay? Type like 1 and then type something in the chat, like 1, use this test. Start typing in the chat answers as I write out tons of questions. I think of well, think of one more here. I think of what I haven't covered. Okay, so these are just on tests on tools and techniques. Okay, so how do you do these types of questions that ask you what you would use? You do them by figuring out what variables you're dealing with. A lot of times it might be what variables, and great answers in the chat. We'll see if we got them right. You ready? So to analyze the GPA of U2 students, what kind of data are we working with? To analyze the GPA of U2 students, what kind of data are we working with? To analyze the GPA of U2 students, what kind of data are we working with? Quantitative. So when you hear quantitative, what do you think? Ooh. When you hear quantitative, what do you think? When you hear quantitative, what do you think? When you hear quantitative, you hear mean. Who's mean? If you're doing drugs. T-test, T-test, T-interval. T-test, T-interval. The first one is T-test, T-interval. So T-test, T-interval. You could do an interval to estimate the truth. You could do a T-test to hypothesize what the truth is. Right there. The next one says we want to analyze the percent of students who will live on or off campus. Is that quantitative or categorical? Percent of students who live on or off campus. Be careful. Because you're like, percent. I know what a percent is. Be careful. And here's where people, so this is where, don't worry, I say be careful, it is proportions. Because although percents are a summary of proportions, and we'll throw some points out here, because when you ask someone the question, do you live on or off campus, it is a categorical question. It is categorical because you have a percent who answer in a certain category. Like, just think about like gender, me being male. Well, there's a percent of people who are male. That doesn't make being male a quantity. But you summarize it. Summarizing data is different than the actual data. When you collect the data on or off campus, the data would look the following way. You'd have right here on, OB, whatever that is, off, and then when you summarize the data, you would get percentages, but the data itself is categorical. Does that make sense? Like, although these are percentages, they are being expressed as the percent that are of that group. The data itself is still categorical. And this right here, so I think, do people know the answer since this is categorical? What are we going to do? We're analyzing the percent of students who live on or off campus. So what is this going to be? What is this going to be? What is this one going to be? People are saying some right answers in the chat, but what will it be? Proportion test, proportion interval, yeah. Prop test, prop interval. You could do an interval too to estimate the true proportion. Analyze the relationship between height and weight. And I gotta say, Bella, really good job this one. Be careful though. Maybe rethink it. So what do we have right here between height and weight? Height and weight, what do we got going on? You might even say something. What do you got going on with height and weight? Height is inches, weight is pounds. You got quant, but what kind of quant? 2 quant, Colin, right there, nice. So Aiden, that's where, and don't worry, Aiden, we're throwing you 5,000 points. The 2 sample T is a little bit different. I've been really mentioning that one a lot. QQ. Kind of, that's kind of what we're doing right here, Grace, a little bit. QQ. So when you hear QQ, what are you thinking? QQ. So what are you thinking? QQ. What's the right thing that you would use right here? Anyone know? Oh, yeah, no, QQ. You should want to say more, and then you'd be like, oh. I'll let it hang for another 5 seconds. Yes, Lainey, you're right. When do we do that? Straight enough. What are you talking about? Lainey's got it. You're right there, Lainey. You got it. QQ, straight enough. No outliers. Plot doesn't thicken. So what are you doing? Linear regression. You got it. You great job, Lainey. Throw Lainey some points here. Linear regression. So linear regression or correlation, things like that. Linear regression, correlation. QQ, straight enough. No outliers. Plot doesn't thicken. How do I erase that other thing? Does that make sense? It's 2 quantitative variables, so it's a relationship between 2 quantitative variables. Brian wants to analyze if students eat McDonald's based on living on or off campus. So what do we got going on here? Analyzing students eating McDonald's based on living on or off campus. What do we got right here? These are called tools and techniques questions. Cat, what kind of cat? So we got, do you eat McDonald's? Rarely, but yes. And then, but not just cat, you're right. Cat's all in the chat, not just cat. Looking for a tiny bit more detail. Tiny bit more detail. You haven't said anything wrong. Boom, Noel on fire right there. You got it, Noel. It is the chi-squared test of independence because there are 2 categorical variables. The chi-squared test of independence has the condition count data, which requires 2 categorical variables. Kind of, but no, Kaylin, you are correct. There is on or off campus, but the chi-squared test of independence could have freshman, sophomore, junior, senior, which is 4 groups, 4 samples, and it could have favorite place to eat, which could have lots of levels, like maybe 10 levels we have. No, but Kaylin, you didn't say anything wrong. The technicality is the chi-squared only requires 2 categorical variables. Now, with what you're thinking about with 2 levels, that will come up here shortly for something that requires comparing the difference. Very shortly, not yet, but shortly. So how about this next one on question number 5? Brian wants to see if students will win once if they buy 100 lottery tickets. What is the right thing you've learned that you would want to test with lottery tickets that are independent from each other on whether they will win at least once? You'd have to use the what? Very tough one here. That's not what we were just doing, but what would you use to see if you win at least once with lottery tickets? The what rule? I'll give it a hint with that. It's one of those 5 rules you learned a while back for test 2. So hints right there. They do need to be random. Good answer. Not random. I'll give you a hint. It's not the addition rule. Someone will get it very quickly with that. That kind of is like, it's not the, well, the 5-number summary would summarize visualizations. Because you're seeing, do I win at least once? And in the at least once problems, you had to use the what rule to multiply things that are independent. You could, Jackson. It's more like these are like very small questions to see if you know how to use what you've learned. The 5 rules are, for, I'll mention that here, someone will probably get in a moment. The 5 rules are, rule number 1, probabilities have to be between 0 and 1. You can't have probabilities negative. You can't have probability over 1. They have to be between 0 and 1. Rule number 2 is the set of all probabilities have to add up to 1. Like if you talk about a 6-sided die, the probability of 1, 2, 3, 4, 5, 6 is all 1/6, and that adds up to 1. Rule number 3 is the complement rule. The probability of A and not A add up to 1. So if you say the probability it's going to rain today is 80%, the probability it does not rain today is 20% because complements are complementary. They add up to 1. Rule number 4 is the addition rule that 2 mutually exclusive events can be added together. So we can say the probability it rains today or the probability it not rains, because those are mutually exclusive, because complements are mutually exclusive, is 80 and 20. And because they are mutually exclusive, which complements are, they can be added right there. The last rule is called the what rule, which says you can multiply independent things. The last rule is the what rule that says you can multiply independent trials to figure out the probability of this occurring and this occurring and this occurring and this occurring. So after the addition rule, we learn the what rule. Test number 2, the multiplication rule. This was a curveball question. It didn't really follow the other formatting. But the multiplication rule states that independent trials can be multiplied together to find out the probability that this occurs and this occurs. So if you want to figure out the probability of winning at least once, you have to use the multiplication rule and technically also the complement rule to figure out 1 minus the probability of not winning 100 times. The last one, though, goes back to the format. That was a curveball question. The last one says we want to look at the difference in sales between 2 stores. So what would we use here? The last one says we want to look at the difference in sales between 2 stores. So what would we use here? Remember, identifying variables can often help. And boom, Aiden's already done it. The 2 sample t. The 2 sample t. Because when we look at sales, sales are quantitative. And we are looking at the difference, which the difference is when we do mu1 minus mu2 between the 2 stores. And 2 stores is where, so Kristen said earlier, I think it was Kristen, about 2 groups. Other than written responses or the questions on the test multiple choice, they look like the Canvas content. Canvas content looks like the test, so check out the Canvas content to see how the test looks. So really good review right here. I want to do one more things with this. On the left side, we're going to say, how would you graph this? So please, if you would right now, take a screenshot of what's on the screen. Does everyone see this? Take a screenshot if you're watching the screen. And we'll call this, how would you graph this right here? So take a screenshot if you don't have it, because you're going to need to reference it. Okay. Well, maybe I need to keep on that screen. I'll leave it over there. Okay. So now we're doing, how would you graph these? We've already cheated this out a little bit. Question number 5 is not easily graphed. It's not beautiful. It'd be visualized with a nice picture. How would we graph the first one with GPA of students? And then explain why. And there are multiple answers to this. How would you graph the first one for GPA of students? Colin, good answer. Not a scatter plot, though. Scatter plots are bivariate, which require quantitative. So a scatter plot is bivariate. You have to have 2 quantitative variables. So scatter plots require 2 quantitative. Caitlin's got a right answer. Nice job, Caitlin. A box plot is a possible answer. So you could use a box plot for it. That's a possible answer right there. Or histogram, classic. And you think when you do this in JUMP, when you do univariate data, quantitative univariate data, you get right here a histogram and a box plot. They also dot plot, stem and leaf, but Hannah got the dot plot. We could do dot plots right there. So you could do those. You could do stem and leaves. If you go right here and JUMP, you can actually get a stem and leaf. Where's that stem and leaf? There's that stem and leaf. Wow! No one loves stem and leaves. They're rarely ever used. We got to teach you them because you might see it one day, so we have to let you know what it is. Now we want to analyze the percent of students who will live on or off campus. So we want to analyze the percent of students who will live on or off campus. So you have to think I'm working with one categorical variable. So you got to look at the screen right here, figure out where you're at. And right there, you can make a pie chart of your favorite bars and a bar chart of your favorite pies up there with 1. The reason there's nothing on the left is because we're not having a bivariate display. So that's what it means over there on the far left is the second variable. The first variable, your primary variable, variable number 1, you select what is that. And if you have a secondary variable, you're inside of the bivariate space. So this is the bivariate space. This is the univariate space up there. I wish I had a full green screen, just walk around here, but I don't. So you could do a bar chart, a pie chart, a Pareto chart, all those things. You bar, pie, all those things. Pareto, which is a bar chart put in order. Ring chart. Lots of answers, that one. Usually bar and pie. Probably bar chart. Brian wants to analyze height and weight. What would we analyze with height and weight? So think, you've already got this labeled. You've already said, well, wait a minute. Height and weight are this. So how would you analyze height? But it merits at the same time. And Bella, you're basically correct. It is scatter plot. It wouldn't be a time plot, though, because time plots are special case scatter plots where we might look at someone's height over time. Like imagine you're trying to see, has my child been growing? And you could do a time plot and you would plot their height over time. The visualization of that would look something like this, where you'd be measuring them at 60, 60.2, 60. Maybe it's like monthly height. Does that make sense? What I'm saying right here is like every month they're hitting a growth spurt and you're measuring their height. You really are good. This is the child's height for a year with major growth spurt. And going, what? So great. They said, Santa, I want to be taller. And Santa said, okay. There's a way to do a time plot here very quickly. I always forget. Quality and process. It's very important I get a time plot right here. Genetics. Never even done that in Jump. No, you can go here to graph. You can do this, and then you can drop it in here in the Y. No. I thought we didn't need the second variable. No, it's quality process. 1 second. I just want to see this. Control chart. These have a different spot for it. Well, if I don't find it in 10 seconds, I'm not going to do it. Well, darn it. Okay, you just go right here. You go month. There we go. Now you go right here, and then you go fit Y by X. There was a quicker way to do it in Jump a long time ago. There we go. There you go. That's a time plot. You can go here, call it month. And then you go here and call it height. Does that make sense? This is now a time plot. The reason it's a time plot is because time is on the x-axis. Special case scatter plot called a time plot. When you have time on the x-axis, time is quantitative because it's how distance of time measurement between 2 points. And that is called a time plot because 2 quantitative variables with time on the x-axis. How about question number 4? We're analyzing if people eat McDonald's and if they live on or off campus. So while you figure that out, I'll visualize it for you. So you got it right there. So Mickey D's, and we'll say Mickey D's, yes, Mickey D's. What else could you do? So what else could you do? You are correct, mosaic. What else? To visualize this, you can do mosaic. Contingency table, yep. And side-by-side side-by-side bar charts. Technically side-by-side bar charts. That one we don't do as much, but mosaic and contingency table, this is chapter 19, which we just did. And you might get something like this right here. So here you would see the relationship between people eating McDonald's and living on or off campus. And here it is right here. And you can see if they live on campus, 69% of them ate McDonald's. And you can do side-by-side pie charts too, technically. We are currently in this space, which I'm blocking, with the mosaic plot and contingency table, which are the two most common, and the visualizations. And we definitely see a relationship with this fake data I just made up right here to analyze if eating McDonald's is independent of living on or off campus. And it looks like we reject the null, and there's strong evidence that people who live on campus are more likely to eat McDonald's. Doesn't mean you eat McDonald's if you live on campus, just means you're more likely, because there's McDonald's right there. And I feel against McDonald's. And last but not least, we would probably not do much for visualization on this question, but we do have the difference in sales between 2 stores. So how would you visualize the difference in sales between 2 stores? How would you visualize the difference in sales between 2 stores? how would you visualize the difference in sales between two stores? I'm making up fake data right here, so you can see the type of data you would get. Sure, fake data, fake data, fake data, fake data. Oh my gosh, that's going to destroy the thing. There we go. And those are outliers. Sure. Sure. There we go. And should have done lowercase. Easier. There we go. Side-by-side box plots, correct. For real this time, Lainey, you are correct. We can go right here to look at sales and stores. Notice, and I said this a bunch of times, when doing the two sample t, what do you have? Two quantitative variables or what? If you do the two sample t-test, you have what kind of variables? You can see it on the screen visually. The two sample t-test will have what? You can see it visually. Great note. Not like it's on the test. Teaching the test moments. The two sample t will have what kind of variables? You can see it there and there. You can see it there and there. One quant, one cat. The X is categorical to create the groups. The quantitative is the T, the quantitative measure we are analyzing. And we can go right here and run a two sample T, and we find out that we do not have evidence of a difference between the two means because the p-value for a difference, I'm using this one for the does not equals test, is above 0.05. And last but not least, and we're going to go back to Moira's sheet, why else do you lack evidence of a difference? Why else do you lack evidence of a difference? Why else do you lack evidence of a difference? Tell me conceptually. Correct. You will look at jump output. That is correct. Why else do you lack evidence of a difference? Why else do you lack evidence of a difference? Remember, we can estimate the difference. You think the difference between the two stores is somewhere between this and somewhere between this. What does that interval include, which would lead you to believe there's not evidence of a difference? I am 95% confident the true difference in sales between store A and store B is somewhere between -24 to 208, rounded. It contains 0. So you're saying it's possible there is no difference. Remember, the null hypothesis is mu1 minus mu2 equals to 0. So what does it make sense to do with the null hypothesis if we estimate that 0 is possible? Very important wording. It makes sense to what the null. If we are estimating that it's possible the difference is 0, and the null is that the difference is 0, then what do you do to the null right there? Very important. Make sure to get the wording right. You don't reject it. Exactly. Fail to reject is great wording. You hear that more in stats than don't reject, which I want to start a campaign like, let's start saying we don't reject the null. Like let's just all agree that from now on, everyone should say, I don't reject the null. You either reject it or you don't reject it. But here's the thing. I haven't won that battle yet. And because of that, you're going to hear fail to reject. People are going to say that. And if I don't teach you fail to reject and someone says I fail to reject the null and you say, what? They say, where'd you learn stats that they didn't tell you that? Where can you find all the tests? The review sheet, review 3 has all the notation on it. Review 3 has all that notation on it. Good question, Grace. So let's pretend we don't have certain values in the output. Okay, you ready? We're going to erase a few values in the output, and I need you to find those values in the output. So pretend the test were to have the following values erased. So you have to know how to get these values. So we're erasing values, although you can see them right now. Pretend you haven't seen them. And we're going to talk about each one of these values and how you can mathematically derive it from the rest of the output. Okay, we're good to go. We have value number, we'll go in purple, 1, 2, 3, 4. Has anyone figured out how to get any of these values missing in the following output? And how do we solve it? So tell me one of the values and how do we solve it? I need one of these values on the screen, and how in the world did you get just, or you could say, man, I'd really like to hear about number 4, number 3, or number 2, or number 1. Now there's a trick one on here, which I expect you to talk to me theoretically on it. This is two sample T output when comparing the difference in sales between two stores, store B and store A, to see if there is a difference. How in the world could we get any of these values? Well, it helps to start marking notation. The difference is the sample mean of B minus the sample mean of A. The standard error of the difference is the formula S sub A, B, or it doesn't matter. Rock knows.
It doesn't matter!
Over N sub A to plus S sub B over N sub B. Caitlin's already said it. The T ratio up there is literally this formula we just wrote over there on the left. If you just take these two numbers and divide it right there, you will get this value. So literally dividing those numbers right there, 92 over 53, literally solves out for this. That's because this value is this value. It is the difference. That is literally the difference. And this value right here is literally this value. And that is the equation for the t-test. You're seeing the t-test equation right there. If we go to the formula sheet, that is the t-test equation right here. Y bar 1 minus y bar 2 minus 0, which is the hypothesized value, but minus 0 does nothing. Rock knows.
It doesn't matter!
Standard error is the formula we also wrote. I'll disappear so you can see it, but the formula is written for you right here, and that will solve it. Okay, so what's another value that we have on the screen? We need to figure out a way to get value 2, 3, or 4. How in the world do we get those? It's everything on the formula sheet. Check out the formula sheet found under Review 3. Go to Review 3, check it out. How in the world would we get another value currently on the screen? All of these require some theoretical knowledge on what's going on. There's a few easier ones. One of them I'm just expecting you to tell me why or why not we can get it. Or you could just ask, hey, Brian, I really don't know how to get question 2 or 3. Boom. Lainey said the next one, the degrees of freedom for the 2 sample t is too complicated. We got freedom in the chat. So we would use online calculators for that. We're not going to have you solve for that. So great job, Lainey. The 2 sample t is too complicated when it comes to the degrees of freedom. We'll show that formula again just because we like showing it here. But the degrees of freedom for the 2 sample t is too complicated. Degrees of freedom, 2 sample t. It is too complicated. You go right over here and you take a look and you go to the images and there, where's that formula at? That's not the formula. Degrees of freedom, 2 sample t. There it is. Oh my gosh, I don't want to solve that. I don't want to solve that. And I think right here, maybe close, Noel. For the 2 sample t, good question, Bella. It's only the 2 sample t. What is the degrees of freedom formula for the 1 sample t? What is the degrees of freedom formula for the 1 sample t? How would you find out degrees of freedom for the 1 sample t? N minus 1. So the degrees of freedom for this, because it's a 1 sample t, is 799. And then I think Noel's working on number 3. Well, mathematically find number 3 and tell me why it is this. When doing hypothesis tests, there's 3 possible alternatives to pick from. The 3 alternatives that we can pick from, we don't use them all, are in order: the does not equals test, the greater than test, the less than test, and the researcher picks this based on their question. You don't use all 3 of those p-values. Jump just gives them to you to say, hey, we ran all the tests, you just pick which one you're analyzing right there. And they have a relationship. Theoretically speaking, if your less than p-value is 90%, or greater, your less than is 90%, then what would your greater than p-value be? If your less than p-value is 90%, what would your greater than p-value be? And notice they point the way they shade. Great job right there. Good job, Bella and Lainey. So what would the does not equals p-value be? Which you can see how a does not equals test looks up here. What would the does not equals p-value be? What would the does not equals p-value be? Not 0.05. You're on the right track-ish. Not have it, though. 0.2. It reflects it on the other side. It takes this and reflects it. It's doubled. Great job, Lane, right there. It doubles it. So that's why. So what's the value of the does not equals test here? The smaller one is half of it. Like, these have the relationship of these add up to 1, and this is 2 times the smallest. So whatever the smallest is, you just double the smallest. So what is number 3 equal to? Just try to solve for what value 3 is and see if you can get it. With that knowledge, be like, oh, 3 would be this. You have to know which one you're solving for, though. Be careful, because it's not always going to be doubling it. Don't just double it and be like, oh, we just double it, because you might be doubling the wrong one. You can see that these add up to 1 because they're complementary. They add up to 1 if you do it right there. So what's the does not equals p-value? Should be able to get it. What do you do to the smaller p-value? Don't worry about being wrong. Basically, nice job, Colin. Good work here and good practice. People are getting it. Yes, you've done it. There it is right there. And there it is. You just double the smaller. People are showing the math. Good work, Jackson, everybody. Thank you, Colin, for being here. Seastorm. Good work. So now we only have one more value. And if you hear the upper confidence limit for the difference, upper confidence, what do you think you need to get the upper confidence? You might need to use a what? So now we only have number 4 missing. You double the smaller p-value to get the does not equals test. The does not equals test is this 2 times the smaller, and it's not, it depends if you're finding the does not equals. So good question, Bella, right there. The does not equals test is 2 times the smaller of these two. That's the relationship that p-value has to the other ones. You don't always double the p-values to find the one you're looking for. It depends which one you're looking for. So, like, let me just ask this really quickly before we go on to the next one. How would you find that p-value if it's missing? There are 2 ways to technically get it. So how would you find the missing p-value now? So now you would find that missing p-value how? There's 2 ways to get it. What 2 ways, if that was missing right there, would you get that p-value? There's 2 ways. Because that's the greater than test. That's what I would do, Anna. That's the quickest way. Because these 2 p-values right here have to add up to 1. So if you know right here, this adds up to 1, you can just subtract from 1. Yeah, that's the quickest way. And then double check linear right there. You would just, but not divide by 2 though. So does that mean, great job. And what's the other way to get this one? There is another way to get this one though. What is the other way to get this p-value? You are correct. Subtract from 1.9447. Because basically you have like the above side and the left side, and it adds up to 1. So you're just trying to get the other side down here. Well, whichever side you're trying to get. That's why you can subtract from 1. Take half. Great job, Anna, right there. Take half of the other one, because if it's 2 times the smaller to get this, you can just divide this by 2, and you see how like you just get half of this. You just take the area and take half, because you're just trying to find the smaller side of the curve. Does that make sense? Because currently visualized right up there right now, you are seeing the does not equals alternative, so you only technically want this over here. Does that make sense? So I hope that helps out visually. And then this is the greater than, because you're going above the t statistic of 1.7. So the t landed at 1.7, and you're graphing to the right of the t greater than the t. That, I hope, like, the more you understand this, you're like, I got this. So let's do that last portion of the output right here. If you hear the upper limit on an interval, then you think maybe I need to have a what to get this. When you think about intervals, we'll use orange. Intervals have a what? So you're trying to find the upper limit on an interval. That's what you're trying to find. Anything else we could use? Well, the center. And what's the center? We don't know what the upper is, so let's put a question mark above this. I don't know what the upper is. What is the center? It's kind of the mean, and margin of error is going to help too. We could use a margin of error. That's plus a margin of error. That's minus a margin of error. There's another thing we're missing. It's good info, good helping us out right here. So we're trying to find that upper limit. What else? What are these values? Well, the interval, it has a median, so to say, but not quite. Lower limit. So what is the value of the lower limit? What is the value of the lower limit? Just tell me mathematically. What is the value of the lower limit? We just got to look at the output. Yep. What is the center of the interval? What is the center of the interval? This is confidence interval, you got it. What is the center of the interval? Does anyone know? Yes, you're right, Kaylin, yeah. And you can actually see this if you look at the formula, because on the formula sheet, it states that this right here is the center of the interval. That is the center of the interval because we're estimating the difference. And not quite good. Anna, good guess and good work, good practice. Not quite, but good guess. And so that's the standard error. That is the standard. The center is the difference because that's the center of the interval. The best guess of the difference, which is where we put the center, the estimate of the difference. So what do you think you can find right now? With the information you have on the screen, what do you think you could find? What do you think you could find right now? We'll write this quantity in a different color to make it like, whoa. Kind of, yeah, keep going. I think people are seeing it. Help me find a value and be like, oh, I found something. This is where if you see it, you're like, I got it. We're 2 steps away from getting the answer. Feel really close. What quantity can you solve? Well, there's a difference in means interval. There's a difference in means. What quantity can you solve for that's on the screen? If we're... yes, Noel. What does Noel solve for? Noel's done something really good. Noel, excellent work. What have you solved for Noel? Noel took 91.82 and minus means plus. What did Noel just get us? Kind of, and this is just the margin of error. It's the subtraction. So that's, we'll just call it 1/16 for nicety's sake. So we just found the... good morning, Colin. Good to see you there. 5,000 points. Pixie Dust from Disney. Colin, so good to see you, and thank you. You are always a ray of positivity. Thank you for sending pictures of Disney and everything. You are awesome, Colin. Everyone give shout outs. Colin's over at Disney. Give some W's, Colin. I'm going to throw a W, Colin, in the chat. And Brielle's already solved this. Look at that. Colin comes in, and in seconds we solve this. That's power right there. That's the power of Disney. So with this right here, what we're going to do, and I think people are seeing it, you would just add this. Does this make sense visually seeing it here? Is you just add the 1/16 because now that we know the margin of error, we can now solve this, and mathematically it'll be this value right here. This is more decimals being carried to, whoops, I'm going to do the orange. But does that make sense how we did this? Drawing it out can be a huge help, and that carries more decimals. So that is carrying all the decimals, but we found the margin of error because from the center to the lower is a margin of error. So good work right there. Well, that's missing values in output. Let's go back to Moira's sheet. We've been kind of working through it, making up new questions as we do it. And it should be still on here. Moira's sheet, where are you at? I think it's one more thing backwards. Here we go. What are the degrees of freedom? How many degrees of freedom formulas have you learned? It should be correct, Noah. It should be accurate. Let me know if you have issues. How many degrees of freedom formulas have you learned? This is a good review. There are... The 1 sample t has n minus 1. The 2 sample t is too complicated. There's one more. If we're going to compare on-off campus and people's 3 favorite restaurants, how many degrees of freedom does that have? Oh, on-off campus, whoops, and 3 favorite restaurants. There we go. How many degrees of freedom does that have? 2. If we're going to compare freshman, sophomore, junior, senior, and then we compare favorite restaurant with 3 restaurants, how many degrees of freedom does this have? So we have freshman, sophomore, junior, senior, and between 3 restaurants. How many degrees of freedom does this have? Freshman, sophomore, junior, senior, 3 restaurants: McDonald's, Burger King, Arby's. No one said the answer yet. Freshman, sophomore, junior, senior, and then Burger King, S got it. It is 6. It is 6. Great job, Candido and Caitlin, and good work and good guesses. That last formula is the degrees of freedom for the what? That last formula I just did right there is the degrees of freedom formula for the what? That last formula. And so modern, really good question. So it's rows minus 1 times columns minus 1. So when you're doing the chi-squared test of independence, you look at this and you say, Brian, this is a what by what matrix. Brian, this is a what by what matrix. Can you tell us this is a what by what matrix? Say, Brian, this is a what by what matrix. So we'll need to call this part degrees of freedom review. Be careful. Is it a 3 by 3, 2 by 3, 2 by 2? I'll tell you what, vote now in the chat and take a vote. I'm about to put them all in the chat. Which one of these is it? So with what you're seeing on the screen right now, Which one of these is it? There we go. Got it marked in the notes. Okay. And we got a lot of right answers. It is a 2x2. Boom, Noel said it right there. Don't count the totals. It is a 2x2 matrix. And people get tricked down here because the 2x2 means there's two answers to do you eat at McDonald's? Yes, no. And there's two answers to are you on or off campus? Yes, no. So that is a 2x2. So to Modern Melon's question, what are we doing right here? When I say 2x2, remember the formula is rows minus 1 times columns minus 1. So 2 rows, 2 columns, subtract a finger, and multiply 1 times 1. So how many degrees of freedom does this have if it is a 2x2? So since it's a 2x2, what has 1 degree of freedom? And there's the answer down there in the corner. The chi-squared is between two categorical variables and has the degrees of freedom formula, rows minus 1 times columns minus 1. You just have to say this is a blank by blank and subtract and multiply the two numbers together. So that is the chi-squared degrees of freedom. What was the first degrees of freedom formula we learned again? What was the first degrees of freedom formula we learned again? What was the first degrees of freedom formula we learned again? N minus 1. And that is used for the one sample t, and that's the way to memorize it. So I'm going to hypothesize that the mean is 79.00125. We usually, someone's going to do that if I do that. I'm going to hypothesize that the mean is, I don't want to do that because everyone does that because they're like, no, the mean is this. I'm going to hypothesize that the mean is this. And we're just going to barely reject the null with the two-sided test being a p-value about 0.046. I'll tell you why in a moment. But how many degrees of freedom does this test have? Remember what you just said? This is a one sample t to test the true attack power of Pokemon, which is quantitative. So how many degrees of freedom will this test have? How many degrees of freedom will a test on 800 Pokemon to test the true attack power of the Pokemon have? How many degrees of freedom will it have? It'll have how many degrees of freedom to test the true attack power of the Pokemon? 799 and minus 1. P-value 0.046 for the two-sided. Oh, it rounds to 0.046. Got it. Now, the reason I was able to do that is because I looked at the standard error and went a little further than two standard errors, because two standard errors would have a p-value of about 0.05 due to the 6895 outside 5% rule. You're not meant to note that in depth, but I've ran a lot of these tests. So I used that quantity right there to cheat and went up basically two standard errors for the hypothesized value, which is right outside the bounds of where we would reject. Notice right here the t-statistic of 2 and the p-value a little bit below 0.05. Can we go over question number 2 under chapter 16, which is that a homework or quiz problem? Caitlin, let me know. We might do that next year. You got it. I've been just trying to fill this video with sections of knowledge. So the repeat it again. When do we use the one sample t? When we are making intervals or testing? Ooh, make sure I think I have that. We'll go grab that here in a moment. The one sample t is used when we're analyzing a what variable. The one sample t is used when we're analyzing a what variable. The one sample t is used when we're analyzing a what variable. The one sample t is used when we're analyzing a what variable. A quantitative variable. And just that variable. No relationships between another thing and this or that. No relationship between height and weight. You just say, I want to know the attack power of Pokemon. You don't analyze a bivariate relationship, or that'd be scatter plots with regression, or two sample t. Last thing we did, and this is just finishing up the review on degrees of freedom, the only other degrees of freedom formula we talk about as a too complicated formula. So the two sample t degrees of freedom formula, we do not have you memorize. We always say, how do we say it? The degrees of freedom formula for the two sample t is what? The degrees of freedom formula for the two sample t is what? I think the output even, or your cheat sheet literally says this. It literally says right here, it says we'll use output. It's too complicated. So you do get the cheat sheet right here, not cheat sheet, formula sheet. It's too complicated. It's too complicated. And that is it right there. You won't solve that by hand. We use applets and stuff for it. I will finish up this Moira's question, which we're pretty close to being done with. We're just going through every bit of knowledge. There's degrees of freedom. This right here, this calculation is the formula obtained from the output above. She goes here and takes y bar minus mu naught. And so mu naught in her problem is equal to 72. They hypothesize value, y bar is equal to, you get it from the output, 70.98. And then she divides by s over square root of n, s over square root of n. So you can see s right here, standard deviation, and n, and she obtains the t-statistic. So, well, you will use it, you just don't need to memorize it. So this is y bar, this is s, that's actually standard error, so you could just use that quantity. And then this is n right there. And then this is the tricky part. This is, we wouldn't do this to you on a test, but we would probably want you to know which of these would be most likely to reject the null. I don't think there's a test question like this, but which of these would be most likely to reject the null? I'm going to grab Moira's test. Okay. Let's say A, Z equals 5 for less than TL. B, Z equals 5 for greater than TL. C, T equals 0 for does not equal. D, T equals 1 for. Okay. Which of these would be most likely to reject the null? I think she sent it out. She's got her sheets and everything. I'll go find it here in a moment. Which of these would be most likely to reject the null and why? And I'm gonna draw pictures of these. I didn't give degrees of freedom. If any stat person watches this in the future, it's just mainly theoretical. So which of these would be most likely to reject the null? TDF or DF, let's say we'll give a DF for a stats person who gets mad at me. DF equals 100 for the T. So it's basically normal stats person who watches this in the future. Would it be A, B, C, or D? Which of these would be most likely to reject the null? We gotta be careful. You're on the right track, Noel. Noel, you're very much on the right track. Noel points in the chat. You're on the right track. But what does less than test mean? What does greater than test mean? What does not equals test mean? When you do the not equals test, like if you say this is a less than test, if you say this is a greater than test, if you say this is a does not equals test, if you say this is a less than test, what do those decide? So I'll put a mark in right here. And then we're gonna do Moira's question here next. What do these decide for us? What's the point of a less than, greater than, not equal to? Well, the sign of the alternative determines what? 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 You're seeing it in action right now. The sign of the alternative determines what? I'm changing the sign. The sign of the alternative determines how we what the curve. The sign of the alternative determines how we what the curve. This is where the test statistic fell, or is from the data. This is changing the sign. Which test we use determines the way we shade the curve. Greater than shades to the right. Less than shades to the left. The does not equal shades both tails of the curve. So the way we shade the curve is determined by the sign. So if we go back here to this, we can draw a curve, and we can put a t over here at 5. We can draw a curve, and remember 5 is basically off the curve because it goes from -3 to +3, and the t is virtually identical. So when you think about this right here, if we were to start at the bottom and have a t of 1 and do a less than test, would the p-value be big or small? For the very bottom, would the p-value be big or small? Would the p-value on the bottom be big or small for a less than test? Would it be very big or very small? It'd be very big because the less than test shades to the left. Remember, when the p-value is low, reject the null. So that's a big p-value. That's not a low p-value. That's a big p-value, more than 50% of the curve. How about if we land at 0? Here's the thing. You can actually calculate the p-value here. This p-value here is very calculable. We'll pretend that this p-value is about 84%. What do you think the p-value is if you land at the exact center of the curve for a does not equals test? Does anyone know? Remember, it shades both sides of the curve? So think about what's going to happen. Thinking about it shading both sides of the curve, try doing it yourself right now. Try shading both sides of the curve from that point. We land at 0 and we shade both sides. So what portion of the curve will be shaded and what percent of that is the curve shaded? It's 100%. Or p-value of 1 if we do it as a decimal. So the p-value here is very what? I'll write p-values like p-values as they should be written. The p-value right here is very, 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 very what? For question number C, the p-value is very, very what? Very, very what? Very, 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 very what? This is like ultimate don't reject the null. P-value is super duper high. It's like you actually landed right on the null value because there's no difference. You landed at a standardized difference of 0. What do you notice about shading above a z of 5? What do you think the p-value would be estimated to be here? The p-value here would be estimated to be what? Because we're shading greater than, because the alternative was we're testing for a difference greater than this. The p-value is going to be super close to what? Just estimate by amount shaded, which you can't really see. It's off the curve. So it's going to be super duper low. It's basically 0. Basically 0. So which one would you reject the null for? B. A is a bit of a trick because A is the less than test, so you shade below the point. Remember, the sign of the alternative determines which way you shade on the curve. If it's a greater than, less than, or does not equals to, you shade the way the sign does. The does not equals shades both sides right there. So the sign of the alternative is very important, which the researcher picks based on their question and helps them determine which way to shade the curve. Less than shades to the left, greater than shades to the right, does not equals shades both sides. So the answer for this question would be, you would reject for question number B because the p-value would be very, very low for that. We don't do a lot of questions like this, but realize that more extreme z's and t's and chi-squareds result in rejecting the null. So let me find Moira's review. Huge shout out. Moira is amazing. And practice test exam 3. I'm getting the practice test route here. Copy. Form sheet. Boom, boom. Look at that. Speed run getting the test. Okay. Are they numbered? The question was, can we do question 12 under chapter 16? How's the question start? I might have lost some numbers on here. Here it is, chapter 16, question 12. Explain the difference between a type 1, type 1, type 2 error. Did I lose it? I think I did. Didn't copy. All right, 1 second, we'll download this. Might copy. Oh, I want to download it. So funny. Download Microsoft Word. All right. Here we go. Explain. Oh my gosh. Ah! I got problems. Here we are with type 1, type 2 error. Let's review type 1. This is going to be good stuff. I know it. Okay. She divided them into chapters. That's really nice of her. That's very good. Moira is a pro helping you study part C. We'll do it right here. We're going to do the full thing and we're going to do a review. And let me mark this in the notes right here. 1:24:13. You're hearing me say it. Probably should watch it right now. And we've got Moira review, chapter 16, type 1 and type 2 error. Oh, okay. So here we go. We're going to start out with one of my favorite things to remember. It's time to memorize. So here we are with what a type 1, type 2 error is. What number is this? I know you've done this a bunch of times, but you're going to become a pro at it. What number is this? And then you know the next question I'm going to ask if you've already been here and you've already done this. What number am I holding up right there? What number am I holding up? What number is that? You know it? I know we know this. It's 1, and that goes with the T. That's a T right there for true. What number is this? What number is this right here? Brady, good to see you there. What number is this? What number is this? Yeah, crazy. We don't even know what these numbers are. Number 2, and that goes with false. So repeat this and write it down and practice it. In a type 1 error, the null is true and we reject it. That's a mistake. No, I did it by accident. In a type 2 error, the null is false and we fail to reject it. So we say it twice, we say the false 2 times. And this starts with the memorization. You have to think, what does this even mean? So imagine I'm trying to figure out if a student's cheated. And the null hypothesis would be they're not a cheater. So what would a type 1 error be? Can anyone explain to me? Where the null is they're not a cheater. So you gotta think through and do your thing here. So the null is they're not a cheater. What happens in a type 1 error? So explain to me the whole scenario of a type 1 error. The null. Kind of like in a type 1 error, the null is true and we reject it. In a type 2 error, the null is false and we fail to reject. But what is this? What does that mean, Mark? No, you're right. The null is true, but what does this all mean? Caitlin said it. Caitlin got it. You're right. So in a type 1 error, the null is true. Remember what I said the null is? The null is they're not a cheater. Did everyone hear that? The null is they're not a cheater. So that's a true statement. That's a fact of the world. But what do you do with the null in a type 1 error? What do you do with the null in a type 1 error? In a type 1 error, with the null, you reject it. So this is where you accuse someone of cheating who didn't cheat. So it's a fact of the world that they're not a cheater. But you think they cheated because you found evidence and you found it mistakenly. You're wrong. In a type 2 error, the null is false. So it's false that they're not a cheater. They are a cheater. But you fail to reject the null, so they get away with cheating because you don't reject the null. You're like, no, I don't know. I shouldn't accuse them. Or you're like, they don't seem like they're a cheater, but they are a cheater because the null is false. So let's look over here and read through these examples. Check it out. Okay. For each of the situations, state whether a type 1 or type 2 error was made. A bank wants to know the enrollment on their website is above 30% based on a small sample of customers. They tested the null that the proportion of customers who bank online is 30%. With the alternative, it's greater than 30%. And they failed to reject the null. What is the only type of error that they could have possibly made if they failed to reject the null? What is the only type of error they could have possibly made if they failed to reject the null? What is the only type of error they could have made? You are correct. Oh my gosh. There we go. The only type of error they could have made is a type 2 error. Remember, in a type 2 error, we fail to reject the null, and the null is false. So the truth is 35%. So yes or no, is it greater than 0.3? Yes or no, is it greater than 0.3? The truth is that it's greater than 35%. So is it greater than 30%? Yeah, it is. So they failed to reject the null, and the null is true or the null is false. They later find out that it's 35% and they believed it was 30%. So did they fail to reject the null and the null is true? Which is what you should do. If the null is true, you shouldn't reject it. So that'd be a right decision. We made the right choice. But is the null false or is the null true? They later find out it is 35%. The null is false and they failed to reject it. Type 2. Type 2. So that is a type 2 error. A student tests 100 students to determine whether other students on her campus prefer soda Amber A or soda brand B. 55% is 55%. They want to find out if the brand preference for A is 54%. 55% of people like brand A. Later, a marketing company tests all students and finds no difference. Now, this is very interesting. So this is very, very interesting. I like what Moira did right here. So, and shouts to Moira. I think she'll have the same answer on her. I didn't look at the answer sheet, but I'm going to look here in a moment. So the student or the marketing company found out if there's no difference, he's got to be, the marketing company would find out brand A and brand B are liked at what percentages. The marketing company would find out at what, if they find no differences between brand A and brand B, they'd find what? It's 50-50, right? So is her null true or false? Ooh, this is so good. Student to determine whether other... finds evidence that brand A is, yeah. So she believes there is a difference when there's actually not. Moira changed, this is a my Pearson question, but Moira changed it in a good way. So the student found evidence of something that's not true. Does that make sense? So the student found evidence that people like soda A at 55%. But when the marketing company came in and found everybody, they did not find evidence of a difference. And everybody is the truth. Like, that's everybody. So her sample came back with evidence of a difference, and there isn't a difference. Does that make sense? The null is no difference. Or the percent of people like soda A and percent of people like soda B are the same. This would be a type 1 error because she found evidence of a difference and she should have not found it. So if the null is no difference, that's what's true. In a type 1 error, the null is true. This is what's true about the world. At the end of these problems, it states what's true about the world. Like, it's a fact that there is no difference. So her finding evidence of a difference is a type 1 error because there is no difference, but she whatted the idea of no difference. What did she do? Because she said there is a difference. So what did she do to the idea of no difference here? Since she said there is a difference between the soda, she whatted the idea of no difference. There should be a word that comes into your mind here. She rejected it. So we rejected the idea of no difference, and we say we have evidence of a difference, but the null was true. There is no difference. The marketing company found out there is no difference. A human resource analyst wants to know if applicants' scores this year on average are higher on the placement exam than 51.5. The candidates last year average, she sampled, 48 recent tests and finds average of this. She rejects the null at the end of the year. So she rejected the null and says she has what is the only error you could do if you reject the null? This one makes it very clear. This one's a bit easier than the last one. What is the only type of error you could possibly make if you reject the null? It literally says she rejected the null. So by rejecting the null, there's only one type of error you can make, type 1, because in a type 1 error, the null is true and we reject it. So she rejected the null, and it turns out there really wasn't that difference. So she made a mistake in saying, oh, yeah, it looks like we're higher. And then it's like, whoops, turns out we're not. Turns out I shouldn't have rejected that null. I spoke a little too quickly here. Morris thinks she is 69% more productive when she does her makeup versus not wearing makeup. When she, Morris and her friends test this theory with a 2. This is so good. Thank you, Moira. When observed and tested by friends, they fail to reject the hypothesis. So what is the only error you can make right now? If you fail to reject the hypothesis and you don't find evidence, then what's the only error you could make? But what about when she found the average was higher first? That was just from the sample data. That's not for the population. Good question, Caitlin. Because the only way you would know if you really made a mistake is to have all the data. And so this one is, because they should have, okay, they don't reject the null. Yeah, so she's not actually 69% more productive. She's actually 48% more productive from somehow the observer for basically a population of time, like over a year, I'm 48% more productive, and then they observe her for like 5 days, and I'm like, well, can't reject the null. So this would be a type 2 error because looking for evidence of a difference, and they failed to reject. So literally failed to reject right there. That's keywords. That's really good. That's good practice. And you can see right here, fail to reject. The B one is the toughest because it literally doesn't say reject or fail to reject. But she found evidence of a difference. She found evidence that there is a difference between brand preference. That's reject the null, that there is no difference. Questions on these? This is good. They are tricky. And it should be type 2, type 1, type 2, type 1. I'll go look at Moira's answer. It's right here. Type 2, type 1, type 2, type 1. Yeah, there's type 2, type 1. Ooh, wait a minute. Yeah, first one. Failed to reject the null when it was false. And then she rejected the null. Yeah, it's type 1. Oh, did I mess up my color coding? We did say that's a type 1, right? So it should be 2112. I think I messed up my color coding. No, it is 2112. There it is, because I did color coding that way. Yep, good. Great job, Moira. That's some high-level decent questions right there. Not just decent. That was like, that got my brain thinking. I was like, ooh. And Moira does a really good job writing it out for you too. So I try to color code things to show like what I'm looking at specifically to come to these decisions. Keywords like we rejected the null. You could only make a type 1 error. So let me ask you one more on this. A company is trying to see if a new product will get them more profit than last year. They have evidence of this and decide to make the new product. The following year, they have record profits. Okay. So, technically, does anyone know what kind of test we're running? I'm asking some higher level questions on this. What kind of test, if you're looking at profit and the yearly profit, what kind of test would you be doing? What kind of test would you be doing? Higher level questions on this. We're still doing errors right now. Or yes, nice job, Caitlin. You are correct. You would test something like the mean of this year, and then you'd have whatever the hypothesized value is equal to some value, a t-test. Like, do we believe, or is there evidence to suggest that the mean will be increased? So we'd look for the alternative that the mean is going to be higher. And we think we have evidence of that. So what happened because we decided to make the new product? Because the null would be that we shouldn't make the product. We need evidence to make products. Evidence is associated with the alternative. So what do you think happened to the null right here? What do you think happened to the null right here? And I'm going to ask a very tricky question next. What do you think happened to the null because they did decide to make the product? Since they decided to make the product, what happened with the null? So follow me on this one. Follow me for this for a moment. You got it. What happened to the null because they decided to make the product? They said, we should make the product. We have evidence. They rejected the null because you need evidence to make product. You don't just say, let's make all these products. Who cares? We'll figure out which products not to make. No, you need evidence to make products. So they're saying, yeah, it looks like this is a good product to make. We're trying to see if we'll make more money with this. So the alternative would be that it's going to increase profits from some hypothesized amount. The profits this year and next year will be greater than some hypothesized value. So now here's the tougher question. So they did reject the null. They did reject the null. They rejected the null. Be very careful. What error was made? Be very careful. I know what you're thinking, but be very careful. So they did reject the null. Be very careful. Like, Ryan, I know this. You trained this well. I know it. Slow down. Slow down. What error was made? What error was made? Got some I'll answer it in a moment, but I want to see if anyone gets it. So it says they made the product and then they had record profits. Well, wait. So, okay, Mary, there's something extra to this problem. Something a little extra to this problem. If we reject the null, what is the only type of error that can be made? So wait, but follow me on this. If we reject the null, what is the only type of error that can be made? Type 1. Okay, so you're like, okay, type 1 error, right? Hold on. A type 1 error is when we reject the null and the null is true. They were looking for evidence that they would have record profits. They believe they have evidence, and so they made the product, and then they got record profits. Does anyone see? Let me state that again. Listen to it very carefully. They were looking for evidence that they'd have record profits. Bella, 5,000 points. Exactly. They rejected the false null. So there is no error. There was no error. So you could possibly make a type 1 error if you reject the null. When you make a type 1 error, you reject the null, but the null is true. So how would the type 1 error look if I change this question to be a type 1 error? So how would this question look? Like, how would I rephrase this to be a type 1 error? The null was that the alternative was profits will increase. The null was profits are going to be at some set value. So how would this question look if they made a type 1 error? This is no error is made, so no error. Right now, the question is written to be solved for no error because they did make record profits. Well, they did. Exactly. Bella sees it. Because the null is that profits will be at some set value that we believe, like the profits won't go up. And so if you rewrite this question, you say the product flopped and profits didn't increase. So now they said, let's make the product, but they shouldn't have. Does that make sense why it's now an error? So now this is a type 1 error. Because I only changed the last part with what happened, what the truth is. The last part is me telling you, which you then see this in the future. Like if you make a product, you'll find out if it flops. You're like, oh man, that was quite the type 1 error. How would this be a type 2 error? What would be in, like, the company's trying to figure out if they should make a product, and it might be harder to find out if you made a type 2 error, but how would this be a type 2 error? This is just good thinking through what are type 1, type 2 errors. How would this be a type 2 error? And thank you, Jack and Noah, right there. How would this be a type 2 error? How would this be a type 2 error? You have to think through theoretically what would happen in a type 2 error. How would this be a type 2 error? Kind of, Bella. You're on the right track. Remember, the company's deciding whether or not to make a product, right? So in a type 2 error, what does the company decide? In a type 2 error, the null is false and we fail to reject it. So if the company's trying to figure out if they're going to make this product, if there was a type 2 error, what would the company do? They don't make the product, that is true, because they're not going to reject the null. So you would say they don't have evidence to make the product. Next year, Apple makes our product and calls it the iPhone and patents, sure, I think that's wrong, and makes it so we can't make it. Okay, so would you say this company, if there was a company like in 2003 or something that could patent this product that's going to be a smartphone with a screen on it, and they're like, yeah, we got this idea for this flat smartphone device in 2003. I don't know. We shouldn't probably, it's going to cost too much money to make this product, though. It's going to cost too much money, too much investment. And hey, you know, we don't want this IBM phone out there. It's just not, we don't think it's going to work. We don't think people are ready for like a flat phone. They want flip phones. It's all about that Motorola Razor. No one's going to want this flat phone. They want flip open phone with keyboard, touchscreen. Touchscreen. People want that tactile sensation, haptic feedback. And you get that from your phone. So this company had quite the type 2 error now. Does that make sense? Because they said, I don't think we should make this product. But if hypothetically they'd come up with the iPhone before Apple, and then they could launch it in a time frame where it would be successful, like 03, 04, I think iPhone's 06 or so. No, iPhone is 07, 08, I think. 07, 08. I just think where I was when I first saw an iPhone. Let's see here. I think 08. What year did the iPhone come out?
Sorry, something's wrong.
Oh,
Please
really?
try again.
I think it's 08. Summer 08. Very important. 07. Dang. 1 year off on that. Summer 07. I was bouncing around between like 06, 07. Here it is. There it is. Man, I remember seeing that and people being like, they used to do such cool. You see that Apple press conference, you're like, whoa, no way. Well, we have done a lot of review today. Really good work. Probably do some review tomorrow. Any last questions here before I get going? I want to brush up on earlier modules, or is this just the latest module? This is all recorded. I let Farfetched, like Pokemon. It is Farfetched. Leak Duck. Pokemon Go. And so really good resources. Let me show you the resources, Farfetched, because I'm probably going to head off. Or if you have a specific question, I'll probably hang out for a moment more. Might go around campus and catch some Pokemon. So if you go to review 3 right here, you will notice, I'm going to say a lot. On review 3, come on, Mubot. Mubot, there he goes. Mubot's telling us in the chat where review 3 is at. you will see really good review videos. I'm going to show you another resource here in a moment on the YouTube's channel. The review of each chapter. So one more review that I have, and I'll drop the link in the chat, is a playlist going over each chapter. Stats start here. I've heard that a billion times about. And 2 sample T intervals. We want that. There we go. Confidence intervals. I'm wearing the same t-shirt. That's a good time. So here is the link, lecture links. These are kind of my no fun lectures. The formula sheet, I'll find that next. Bella, good question. So these are lectures right here where I go through and I just straight teach you the material, going through, talking about how confidence intervals are done, the z-scores, the interpretations, the theory behind intervals, confidence interval for the mean with T and William Gossett, the conditions, the nearly normal condition, all these things right here. My hair looking all crazy again. How much have I changed in a year? This is basically a year ago and 10 months ago. Yeah, it's 11 months ago. Right at. I came in right before the semester started. And so check out these videos right here. They're really good. And the last ones are going to be the chapters you're going over. I'd also highly suggest going over the speedrun videos. They're a little more fun. They got a cool intro with epic speedruns. Your epic speedruns of statistics. Brian Stevens. Maybe plan to come in, might have some meetings and stuff. Also check out these videos. They're more serious. It just depends on what works for you, what keeps you motivated, what keeps you activated. Then we have test question reviews, and this can all be found in a review 3 going right here. I think I put more things at the end of this playlist. I mean, I figure people will go to the playlist and check it out. But also go here to office hours if you want. That's got 400 views. That's good. 500 views in a year. Not bad. Not bad. I'll take it. We got 19 people watching right now. Hello, 19 people. And I believe it was probably this one. I think it's this one. My Cornell hoodie. Nope. That's not it. It's funny because like some of them I'm like, I really want people to watch this one because it'll really help. This is the most recent one. Here we go, December 3rd. Everyone knows which one. It's December 3rd. Caitlin, thank you so much. You found it all right before me. Yep, here's the full formula sheet. So I go over the full in-depth formula sheet wearing my Batman t-shirt, and it's broken down by section. So I'll go over every bit of the notation. I should have maybe timestamped that a little bit later. But you can fast forward here to where I'm writing it out. I'm explaining it, and I highlight everything as I go through it. I talked about what the problems would probably state, and just understanding where everything comes from and all the notation. I would definitely write these down as you do them. Oh, you're fine. Big Pokemon fan? That's awesome. I'm trying to think, what have I had recently? What is your top Pokemon? I'm gonna pull up Pokemon Go here, and then I'm gonna go on a Pokemon Go walk. I'm gonna pull up Pokemon Go while Brian in the background. Do you play Pokemon Go, Grayson? Tony? Sorry, I saw Grayson at the end, the name right there. This is chill moments with Brian right here. Chill moments. Been playing the Pokemon. Oh yeah, part of PC TG. My wife played that a little bit. One time I ended class and got a shiny right then. Show me shiny Meow. Oh, it's just a regular Meow. They can't even see it because of the green screen. This is, I'll tell you why my wife hates Pokemon Go. My wife hates Pokemon Go. You can go. Ah! It's all my shinies. You can't see it because the camera's blurring. But I have 1,286 shinies. I switched my shot. Oh, wait, there it is. Yep, there you go. You can see here, like 1,086. My wife is like, that's, no. She's like, no. That should not exist. Should not be that shiny, like, Ultras, and Gyarados, Mewtwo's, like, getting all that right there. Jam Grades should be hosted in less than a week. We gotta get it pretty quick, though, because grades are due. Grades are due. Shiny, Zapdos, Brian's Ocean Bunny. That was Parker trading me that one. It'd say, like, Parker right there on it. And shiny. But, awesome. Well, what are my here's my number one Pokemon is like Pokemon Go. Yeah, it's totally fun. I love Pokemon Go. There it is. That one I caught. It's got a Steam Expert Cup, which is a white in Stillwater, Oklahoma. And Pokemon. Maybe look at how many I have. I have like 8,000 and I have 7,850. Keep up in my Pokemon storage. It's like, that's the thing that my bag storage is like 600. So, and then I got I have a Hundo Groudon too. Nice, Brady. If you want, on the Discord, with someone drop I'll drop my Pokemon Go code in there again. As like, there's one Pokemon. Got all the packs. But also, I have a ton of what are they called? Celebies. One's from Ultras. Did that with like Larry and Ultras. Bunch of this or that or whatever. They almost look like they're shiny with the green screen messing up some of the colors. But yeah. Nice job, Brady, right there. I'll go around campus playing Pokemon. Oh, someone put a lure on this stuff. You know what I'm gonna do? I'm gonna put a lure on the other stuff. I got a ton of lures. This is kind of, I never use my lures because I'm just like not around people. I wish it would just work and not blur. But I have something like multiple, like 30 lures of each. The regular lures, I have 27. So let's put a regular lure out for them. Let's just do that. Okay, good. So who's ever here next to this on campus gets a regular lure. Yeah, if you don't have Evalte or I'm not about it. Oh, I got those, I think. No, I'll head off here. I'm just chilling. Got an event at 2:30. Yeah. Oh, this is a guy traded me this. I got a lucky, shiny. I don't even know how to say its name. The one you said, the first one you said. I feel like this is gonna get it better and not blur. But got a lucky. Yeah, that one is really cool, and it's lucky, which you have to trade to get lucky. So I wish it would show up. It's gonna show up. You can do it. You can see it flying around right there. I've got 6 of them. That's why I was like, you shouldn't have that many. I think I have the other one too. That's from Christian Chris. He's a big time player around here. He's got a insane amount of Pokemon. Yeah, I don't have a shiny of these. Man, this one will be really cool right here. The second one. That one just looks so cool. You can barely see it. But yeah, I'd love to get a shiny of that. Oh, is it gonna do it? No, not gonna show up. But I'd like to get, that'd be cool to get a shiny. But yeah, just fun. It's fun to like go around, meet people, play Pokemon Go. Enjoy your time, you know. So with that, drop your Pokemon Go on the Discord if you want. I'll delete some friends. I've been playing way too long. So Pokemon Go. See me around campus, say hey. Bye for now, everyone. Bye.
Hey Brian, what's up?
Hey, Adam.
Oh, what's this?
Adam, what are you doing? Adam!
No!